Thank you. Being placed into conference in muted mode.
On behalf of CMC Microsystems and all of today's presenters, I want to welcome all the participants to this webinar about FACT services. It's a program that delivers micro and nano fabrication and characterization services for development. Just for your information, today's webinar is being recorded and will be made available for download in the future. Today's webinar is entitled Etched in Stone, Advanced Lithography Services for Micro and Nano R&D. This is the first of 4 webinars this year in its series, each focusing on one set of capabilities for nanofabrication. Over 40 people are registered for this webinar, so I think we're in store for a very good discussion. My name is Andrew Fong. I'll be moderating this webinar. I'm a client technology advisor at CMC Microsystems. I'll open by introducing Canada's National Design Network and CMC Microsystems, in particular FACT services, how the program works, and how to start a project. Very exciting lineup of content today. You'll hear from engineers at 4 of the labs in the FACT network. From NanoFab will present an overview of some advanced lithographic techniques that are offered through FACT services, and then each lab will showcase examples of in-house R&D projects, which are enabled by a particular lithographic capability. So film lithography for microfabrication will be presented by Alireza Mezgar from BCM at Polytechnique Montreal. Direct write laser lithography presented by Marie-Josée Gour at 3IT Nano Lab at University of Sherbrooke. Lithography for silicon photonics presented by Edward Xu at the NFC at University of Toronto, and beam helium gallium focused ion beam presented by Aaron Xu at NanoFab, University of Alberta. Welcome throughout the presentation, so please use the chat box on your screens to send comments or questions to CMC host. CMC Microsystems is headquartered in Kingston, Ontario, Canada, with additional offices in Ottawa and Winnipeg. The mission is to enable and support micro nano systems knowledge by 2 key elements: national infrastructure and a path to commercialization. These form the core of CMC's mission, with a 10-year outlook to a thriving advanced manufacturing landscape in Canada. And within this framework, CMC acts as an honest broker of technology and know-how. CMC manages Canada's National Design Network, which is a community of faculty members and students at more than 50 post-secondary institutions across the country. Additionally, we have several facilities in the micro-nanotechnology space at universities, several companies in Canada, and industry partners and suppliers all around the globe. The CMC deliver for prototyping? Last year, saw the numbers that you see in the bottom half of your screen. 200 CAD tools, more than 400 prototypes for academic and industry clients. And that's all in addition to a lone pool of test equipment, training events, webinars like this one, joint projects and infrastructure installed at universities. Clients can access all of CMC's offerings with subscription. In CMC's portfolio for prototyping, services delivers R&D solutions leveraging university nanofabrication labs. URL at the bottom of the screen use a recording of a previous webinar using FACT services and the labs involved in the network. Let me ask you, where do you see yourself in this scenario? the left is a company looking for early stage production. On the right is a university researcher with a new invention seeking stable processes to improve its reproducibility, improve its performance. So both parties want proof of concept. Concept from concept to design, or taking the next step from design to prototype. And maybe for a number of reasons that they need this capability. They need expertise, additional bandwidth, or access to a lab with special capability that's equipped for a more exploratory process development. Or perhaps it's a technology with commercial potential and needs to be positioned for production. So where the needs may be, Fabrications connects the technology developer with a network of labs that are equipped to meet these kinds of needs. The net is open to growth, and CMC welcomes contact from labs who are interested in being part of this initiative. This can include design consultation, development of a process flow, custom fabrication, even low-volume production. Staff in the labs bring years of expertise in a number of microtechnologies. On the website, you can download the full catalog of service capabilities. Getting with Fact Services is easy from the Start a Project page. Every project progresses with the involvement of the client directly with the delivery team. So the client can start the process by sending a request form with details of the services requested, putting some critical specifications and information like the number and type of samples that are required. The academic client requesting service will then engage with CMC to build a dedicated project in consultation with one or more of the labs in the network. Academic clients can also apply for a subscriber discount. Then it is implemented in labs. Will share a common service protocol for quality. And for commercial-facing technology, projects can benefit from alignment and compatibility with downstream partners for production and manufacturing. That concludes the introductory segment. Now I'll hand things over to Aaron at the NanoFab.
Hello, everyone. So my name is Aaron Rishu. I'm a fabrication group leader at the University of Alberta Nanofab facility. For the next minutes or so, I'd like to give you an overview of some of the techniques that we have available to you as fact services clients for nano and micro patterning techniques. Although we've said in the title that this is lithographic techniques, I'll be covering some topics which aren't strictly speaking lithography. So I'm going to go over photolithography, direct laser lithography, beam lithography, nano lithography, but also direct milling techniques such as focus line beam and hot embossing. Now, for this, I want to place emphasis on more practical considerations. You can look on Wikipedia or take a course on general nanofabrication techniques and get an idea of what the state of the art is. But what I'd like you to know is what are some things that you should keep in mind when developing a process flow, when designing your devices and your layout. Things will make your job, lives and our lives easier when actually doing this project to help maximize the success. So, lithography is the process of inserting some kind of a pattern into a layer of resist. Resist can be used as a mask for a subsequent step, whether that's etching or depositing material. Originally developed for print making for art, and in fact it's still used in to make fine art prints. On the micro-nano scale side of things, though, there are just 4 kinds of classes of lithographic techniques. So they start with some sort of source, whether that's photons, electrons, ions, some kind of radiation source. Now that beam of radiation is collimated or steered by some kind of what I'm calling an optical system. For the first of those, it then goes through a mask. This is something that is opaque to that type of radiation. For direct write system, there is no physical mask. This is something that is controlled by software. So this is steering a beam of light or a beam of electrons or ions. After that, the rear, which is some kind of some material, usually a polymer, which is affected by the exposure medium, exposure radiation, and it leaves the pattern, which after developing will give you a transfer the pattern onto the resist. So services I'll be focusing just on the contact and direct write methods. We have standard ultraviolet, deep ultraviolet contact lithography, as well as a variety of direct write methods, including electron-beam lithography, direct laser lithography, and focused ion beam. Sizes of these substrates which we can accommodate, this varies from very small ones on the order of a few millimeters square, all the way up to 6-inch wafers. Lithography, one of the more basic techniques. Services we offer standard H and I line ultraviolet lithography. These are in the near UV at around 365 and 405 nanometers wavelength. Our contact aligners are manual loading, and wavelength gives you a resolution of around 2 microns, depending on what you're resisting. This is a practical kind of lower limit to keep in mind when you're designing your mask. You can maybe push that to 1 micron if you with a bunch of effort. I guess small pieces up to full wafers are capable of being patterned in this technique. A variety of photoresists which are available for different applications. Everything from some general purpose positive tone resists around micron thick, which can pair with lift-off layers to allow sharp line features for layers which are deposited later on, down to more specialized things like thicker resists for ion etching, deep silicon reactive ion etching, some more aggressive etch techniques, as well as permanent resists are cured, exposed, cured, and then remain on the mask, remain on the substrate to form your devices. So just as a reminder for those of you who aren't aware, the tone resist describes the behavior when exposed. So the nice mnemonic is, for positive resist, what shows goes. Anything that is exposed after the element is going to be removed, whereas negative tone resist, the opposite. Only the exposed feature remains. So depending on which tone you want, that's going to depend on the type of process that you're interested in, the sparsity of pattern, also determine what the mask you're going to design. So we'll go into a bit of that more later. Any one of the engineers from the labs or CMC can give you some advice about which resist tone might be best for your process. Now, these layers are liquid and spin coated onto your substrate, and then cured to remove the base of the solvent. The exception is this dry film photoresist, which can be applied by a lamination method. I'm going to leave Valerie from GCM Lab to give some more explanation about the photomasks. There are the first thing to read is that you've got to make sure that your substrate of the mask is going to be transparent to the type of lithography you're interested in. So for our general ion H line lithography, a simple soda lime glass is usually sufficient. If you do deep UV photolithography to kind of push the resolution down below a micron, you will need to get a more expensive fused silica substrate. So about 100 nanometers or so of chrome is sufficient to make it opaque to UV light. And there are two things to consider, again, when you're making a mask. In terminology, you've got polarity and orientation. So for a polygon, you can decide whether that's be inverted or non-inverted. When you're ordering your photomask, non-inverted will be anything which the polygon is going to end up as glass at the end. And inverted one, the polygon will be remaining as chrome. Need to keep this for the orientation. With patterning the front or the back side of the wafer, this will be you can either flip the feature on the vertical axis for this is the right to read chrome up. So when you're looking at the back of the from the side of the mask, the feature will appear the same as your pattern. Right read chrome is what it looks correct if you're looking through the top. So again, which mask polarity is going to be determined by the resist and the type of patterning process that you're interested in. Some things to keep in mind when you're designing a mask, especially for dark field masks, which are mostly chrome. If this you're interested in aligning to another layer, it makes it much easier if there are some windows to view the wafer edges. This allows you to do some very gross alignment. And coarse alignment marks, X, Y, and rotation, actually by eye without needing to use the alignment optics. This could be close enough that when you do bring in an alignment microscope, you can have some linear alignment marks, which would be typically patterned below here, too small to see in this image. This allows you to do your fine registration from layer to layer. Now, if you have the ability to some flexibility with your design, building a sort of 5-micron error, that makes the registration easy. 2 microns, I would say, is a pretty good low limit, and if you really need less than 2-micron registration accuracy from layer to layer, it may be possible with verniers. Sure. And you'd also need very good temperature control because we're talking about half a micron of registration over a 5 or 7-inch mask, for instance. So temperature control would be important in that case. So for again, just for straight size for standard 4-inch wafers, 5x5 mask is possible. We do also accommodate up to 7x7-inch masks for 6-inch wafer processing. So that essentially brings us to the end of photolithography, which is a parallel process. You expose the wafer all at once through a mask. Now, the UV exposure direct right counterpart of that would be direct right laser lithography. So this technique, sort of illustrated here, you raster your beam across your substrate, only exposing the region that you want, and depending on the tone of resist, this can, in this case for a negative tone resist, after development, you can leave a structure. So I will leave it to Marie-Josée to give some examples for laser lithography done at 3IT, but these are just some illustrations from negative tone resist. You can very high aspect ratio structures. This is direct writer really shines, especially for quick prototyping. You don't need to make a different mask every time you want to make a small tweak to your design. It does also allow grayscale lithography to give 3D structures instead of just a straight sidewall structures resist. But the trade-off is that it's a serial process. So it can be hours, usually per exposure, sometimes a day, in order to raster your beam and expose over a large area. Now, direct laser is also the technique which is used for our in-house fabrication of photomasks. We can accommodate an online submission of your GDS2 file specification for your masks. We can take care of that for internal fact services projects. You don't need to supply the masks if you don't want to. We can make them for you. Moving on, electron-beam lithography. This is another direct right method, but now we're moving away from photons as the source to electrons as a source. So now, in this case, this is essentially a scanner microscope that's been souped up. There's an added dedicated hardware pattern generator. There's a beam blanker to turn off the beam when you're moving the stage, and there's also a laser interferometer stage control, which allows you like nanometer type of resolution in the stage motion. Now, it allows you feature sizes down to about tens of nanometers, and also alignment accuracy around that same length scale. It's again a serial process, so you are looking at minutes to hours of exposure, depending on what type of exposure, the resolution you want, and how carefully you want your exposure pattern to resemble your your intended design. So you can have some edge roughness or some distortion if you're if you're trading off, for instance, a rate exposure time for fidelity. Now, a large difference between photolithography and especially electron-beam lithography, proximity effects. The local dose is going to depend on the entire pattern. So this is sort of illustrated here. As you increase your the acceleration voltage for the electrons, they will penetrate deeper and deeper into the substrate. As you, for instance, shown here for a 30 kilovolt beam, you have a lot of secondary electrons which are also exposing the resist quite far away from the beam. So even if you have only a couple nanometers prime beam, you'll be to 10 nanometers possibly with the for your ultimate resolution. For pattern generation, you can use GDS2, which is a standard. Now, natively, that contains no dose information, as opposed to photolithography, which is by on and off. For lithography, you really have to tune the dose carefully, which is going to be very dependent on the entire pattern. It requires several different iterations to do. Different sensors can have different overall doses. So there are different ways to do that. One method, if you have a Wraith type of system, is we've developed a Wraith GTS2 MATLAB toolbox, which allows you to generate complicated patterns, view them, and then be read in natively into the Wraith pattern generator. This also allows you to have finer control over the type of beam. You can register a beam in a circle for curved elements, for instance, instead of treating them all as polygons. There are a couple different exposure modes for e-beam lithography. Normal exposure, the stage is stationary and can write anything within a certain field of view, or what we call a write field. So this is an example here for a structure which is larger than the write field. The software will parse it into several different write fields. Stage will move here, write this, move over here, write this structure, and repeat for the rest of the structure. However, at the write field boundary, there's a possibility of a so-called stitching error. So this error, the stitch and beam do not quite line up. It's quite good stitching error. We have about 20 meters, less than 20 nanometers on a 100 micron write field, and this is in PMMA. Now, it can absolutely not tolerate any type of stitching, for instance, for a photonic applications where you have long waveguides. We also have a fixed beam moving stage approach where the beam is left blank, but the stage is moved to create your pattern. Interestingly, by definition, this has zero stitching errors, but there may be some possible periodic or non-periodic defects just due to the stage motion, jitter, and so forth. So, services, the e-beam lithography capabilities we have, offering from a millimeter to inch full wafers. For the subjects, again, the amount of time it's going to take to pattern a 4-inch wafer will be very dependent on the density of the exposed area. So realize that, and realize that you may take several process iterations to enroll your design. So we have dedicated 30 and 100 kV EBL systems, and I'm going to leave it to Edward to give a description of EBL for silicon photonics at TNFC. Now, to at least in the tool layout is focused ion beam. So this is not, strictly speaking, a lithographic technique. Rather than patterning a resist, we are directly milling, sputtering away some material using a focused beam of ions. So the column is very similar to that of an SEM, but rather than a source of electrons, you have a source of ions. This can be gallium is the most typical one, but also other metals, and helium and neon, for instance, for gas sources. One benefit of fib milling is that the large, heavy ions have only a few tens of nanometers of penetration depth. They're really only hitting the top surface of or getting embedded in the top surface region of the substrate. So for kV, only tens of nanometers, whereas in the previous for electrons, you had something more like microns of penetration. So this is, this allows you, or this can be a bad thing. One thing is that since the ions can remain implanted in your surface, you can have defects in that surface region, local heating, surface amorphization, and if you're gallium, those gallium ions can remain implanted in the surface. So that may or may not be a problem for you, depending on what you're doing. If you're interested in photonic devices, well, that gallium is going to cause optical absorption, which could be a problem for you. Now, the sputter field, fast you're able to mill the material is going to vary widely over, depending on what element you're looking at. Gold is one of the fastest to mill. Chrome is quite slow. Silicon something in the middle. And a consideration is that when you're looking at insulating materials, trying to mill those, you can have a problem with build up. You're implanting these ions, which can then affect the beam later on. Now, this can be overcome to some extent by using charge neutralization with a low-energy electron flood gun. And this is illustrated with these imaging. This is a lithium-ion image of a completely insulating material. It's some zinc oxide rods on a cellulose fiber. Using the flood gun, we have nice contrast, no charging really available, really visible. Try to image the same thing on a very good fancy microscope. You have lots of charging effects. You can't see a lot of the fine structure. Related technique to fib milling is fib-induced deposition. So for this, you have some adsorbed precursor gases, which are broken down by secondary electrons in the very near vicinity of the primary ion beam, and this allows you to deposit a variety of materials. For instance, at FACT labs, we can deposit tungsten, platinum, and carbon. Now, another consideration for if you're interested in photonics or plasmonics, the platinum that you would be depositing, the tungsten to have quite a could have a substantial carbon, so could also induce some absorption, optical absorption in that. We'll be later on talking about an example of some nano-patterning capabilities that we have at the NanoFab using our newly installed dual beam helium and gallium fib tool. The last two topics I'm going to describe are not the previous ones, and that there is no exposure source. There's no radiation source, essentially. So these mechanical methods of patterning. Imprinted lithography, which is conceptually quite easy to visualize. You have a mask. You have a master mold, which is a mechanical mode, which a mechanical tip of something like silicon or quartz, which patterned with the other structures you want. This is into the resist. The resist forms the holes, and that's cured in some way, either with being it above the transition temperature of the resist, allowing it to flow, and then cooling it again leaves those features imprinted in the resist. There's also a ultraviolet lithography in which the photosensitive UV NIL resist is cured and then removed. After both of these techniques, there's going to be a single layer which needs to be removed, either usually with some sort of dry etch, an anisotropic etch, to get down to the bare substrate. You can see that one definite benefit that this has is extreme low resolution. You're limited really only in terms of how well can you make your mask. There aren't going to be any diffraction limit effects that you see with lithography, or any proximity effects that you can see with lithography. This gives you high throughput. You can, once you pattern your master mold, you can use that wafer to wafer very quickly at low cost, but the cost of the mold can be quite expensive. This is an example of some work that was done to make some. So these are silicon oxide pillars capped with a chrome that was used for the etch mask. These 100 nanometer pitch were then used with thermal nanolithography to make a lift-off template, which later used for gold deposition for sensors. That's courtesy of Rob Peters from his thesis. So I guess the concern to be for nanophotography is that you need to have an anti-adhesion coating. Detaching pros want to make sure that the mask is easily detached without lifting up the resist. And so FDTS styling of the master can help in that regard. Now, really similar to NIL, but at a much larger scale, is that of hot embossing. Here is that we don't have a resist. We are directly mechanically patterning a polymer substrate. This type of thing is for full NIL, though. You have a mask, you heat it up, you apply pressure, and it imprints your structure inside of the polymer substrate. The masks can be made with either silicon or, for instance, nickel. Nickel is very robust, but they're expensive, and commercially, I'm not aware of through fab services. I don't think we have any in-house fabrication methods for those. Still, however, we can make in-house. Examples from the Bacchus group at the University of Alberta previously done. You're looking at sort of microns of length. So here it's about a 10 to 20 micron microfluid channel. But again, this is high throughput, low cost. Average features. In fact, if you machine a master mold from aluminum or metal in a machine shop, there is no siliconization required. And this is very easy, but now we're going to mainly the microfabrication. Just in summary, we have a wide variety of lithographic and other lateral patterning features for the micro and nano scale available through services. I will now pass my counterparts at the other labs for some featurette application examples. Thank you.
Thank you very much, Aaron. While Ali Reza is getting set up, I just want to remind the audience that your feedback is welcome. If you have any comments or questions, please send those to CT host using the chat box in your window. Go ahead.
Okay, thank you, Andrew. My name is Reza Miskar. I am research associate with the Microfabrication Laboratory of Films Group, GCM, in Montreal Polytechnic. Today I will give you an overview of dry film lithography for microfabrication. Dry resists have been used in printed circuit fabrication for a long time. In a dry resist, the photopolymer film is sandwiched between two protective films to protect it from contamination and oxygen. Film photoresist is applied to a substrate by hot roll lamination. Before the lamination, one of the protective films is removed. The polymer film is pressed on the substrate. The photoresist film sticks to the substrate due to the heat and pressure of the hot roll. The second protective film can be kept until the development step. Depending on the photoresist composition, it can be exposed by UV light or X-ray. Then is developed by the appropriate developer. The dry film photoresist has several advantages over spin-coated photoresist. Dry normally have excellent uniformity. There is no edge bead formation, and consequently, there is no need for edge bead removal. It is very safe to use as the user is not exposed to solvents. It is stackable to form thicker films. It is much more resistant for etching and electroplating. The great advantage of it is its good topography coverage that's difficult to obtain in spin coating. Preferred sample shape contrary to spin coating. Availability of dry films in various widths and no need for spinning the sample makes the handling of large samples much easier. Coating, around 90% of the resist is wasted. On the other hand, the dry film waste can be as low as 30%. As is perfect, there are several challenges in using dry film photoresist. Thinner than 10 to 15 micron do not exist. This all limits the best optimal resolution. Depending on the process, removal of dry film photoresist can be problematic. That's to be considered in the process flow design. Dryers are used in many applications such as PCB fabrication, electroplating, bonding, and packaging. In applications, they can be used as the layer for dry or wet etching, as a resist for MEMS and microfluidics, as a lift-off resist, and in TSV fabrication. Generally, very convenient for rapid prototyping. Now, let's see a few examples. We have used a 30 micron thick FX930 from DuPont. It has used as a protective film DRIE carrier wafers for small samples. So the best resolution that we have obtained is 20 microns that you can see on this EM image. We have used it as a mask in silicon DRIE and have obtained a selectivity of 100 for Bosch process as 20 degrees. At 20, the two pictures show the results after etching. The film photoresist that's used in our lab is the 500 micron thick SUEX to fabricate microfluidic molds. And you can see the results in the bottom right picture. Equipped with common photolithography and electron-beam lithography equipment and materials. Our facility is open to academic and industrial clients. You are welcome to visit our website or contact us for more information. Thank you for your attention.
Thank you, Isa. Let's control over to the presentation by Marie-Josée.
Hello, everyone. I'm José Gould from 3IT Nano at University of Sherbrooke. So, like all the other fact labs, we have everything in-house to do FIB, e-beam lithography, photolithography. We have contact aligners, deep UV flutter, some spin coaters, a spray coater, and we also have dry film capabilities like Alireza just explained in more detail. And we have two maskless systems, one being with a mercury lamp system with the fancy optics, and another system which is a laser beam writer. So at 3IT, we believe that the lithography is really the building block for all our processes, so it's important for us to have the right resist for the right process. So we have a very broad variety of resist and various coatings that we have in-house that can be used by users and for any external service that we do. One thing that we do have that the other labs do not have is we have a proprietary evaporated e-beam resist that's biocompatible, SR5. So let's focus on the direct laser writing system. So we have a DWS66 system from Heidelberg. It's a 375 nanometer laser at 8 milliwatts. So the minimum spot size is 500 nanometers. We have various levels of gray and high resolution in terms of positioning the sample. Different optical heads that we can put on the system to obtain different resolutions. This is usually the system that we use for making masks, direct laser writing on delicate substrate that cannot sustain a direct contact with our contact aligners. Anything that requires very high accuracy in terms of alignment or even a very small patterned 1 micron and that you can obtain with standard lithography. And finally, we can do 3D resist patterns with the machine. We usually take GDS2 and CIF files that Aaron had stated before that you usually use for mask making. If optical alignment is required, then a simple cross with a 2 micron wide line, 10 microns long, is what is the best. Big markers just means coarse alignment. Now, we can expose pretty much any eye line type resist. This being said, thin resists are easier to expose than thicker resist. It's just a question of ease of the laser to expose all the thickness. But we have exposed very thick resist. For example, if you see the CMOS at the bottom, it was exposed with a 13 micron thick resist. This sample was an existing CMOS device that we had to process after it was made. So we didn't have any alignment markers. It was passivated. It was very difficult and challenging to align. So we managed to do that on this sample. So this is the type of thing that we can do with a laser writer. Bear in mind that we can do other things, but the more resolution you need, the longer writing time you have. So here's another example of what we've done for 3D writing. So gallium nitride-based LEDs have a very poor light extraction efficiency, just because the refraction of gallium nitride is very high compared to air, so the internal refraction is very high. So an idea was made to try to mimic the bell of a firefly onto an LED. So a normal layer was put on the gallium nitride with just a plain layer, and we've also done a structured layer, a rooftop pattern, like you see right here, and we managed to have a 3% efficiency increase from a usual planar layer, and if you compare just to a bare LED, it's a 54% efficiency increase. So there's a lot of things we can do with laser writer in terms of patterning the resist, whether it be really fine features, high accuracy, delicate substrate, or fancy 3D patternings like this. If you have questions, inquiries, whatever, please don't hesitate to contact me or Andrew. Here are my coordinates. Thank you for listening.
Thank you, Marie-Josée. As the passing to the next presenter, I want to field one question that's come in. This would be directed at Marie-Josée. The question is, what is the resolution of the laser writing?
Can you repeat that?
What is the resolution of the laser writing?
Actually depends on the optical head we use. We have 3 optical heads. The final one that we have is a 2 millimeter high definition, and that's 1 micron. And we have, so of course, the lower the resolution, the higher the resolution, the higher the writing time. We also have a 10 millimeter optical head, which has a slightly higher resolution of 2 microns, and we have the 20 millimeter optical head, which has a 5 micron resolution. So typically we select the optical head, which is more convenient or appropriate for the design to be written. It's pretty much the same thing when we do a mask. So let's select the right head with the right design.
Okay, very much. So I'll pass the presentation on now to Edward Xu at Toronto Nanofabrication Center, who will present about electron-beam lithography. Go ahead, Edward.
Yes, I thanks that Andrew. Edward Xu, and from University of Toronto Nanofabrication Center. Today I'm going to give a brief talk about our capability on lithography and applying this lithography combined with our latest DIE etching tool to make the silicon photonics structures. The EV tool that we have is the Vistec EBPG 5000 plus model. Right now we have the layout beamer that can do a lot of things to optimize the exposure and do proximity corrections. And the capabilities we have can do then from 3 by 3 millimeter to 4 inch. We can do up to 6 inch circular wafers. So this is like a semi-industrial E-beam lithography tool. So if you see here, you see the capability can go down to 7. Actually, our latest breakthrough can go down to 5 nano with the HSQ resist. And the field size really big, 560 by 560 micron, and the beam energy is 100 kV. So you really guarantee a good resolution. Stitching error around 18 nanometers. And the good thing about this tool is that the writing speed is really fast, can up to 50 megahertz. Many of the big patterns from, for example, University McMaster, the ends of nanodots to write, so it only takes 2 hours. So it's fast writing for large scale of pattern generation. Tool can hold up to 10 different holders. So if we have a lot of work to do, we just load into the system during the weekend. We can remotely log into the system and control the writing, change the holders from one to another. The line files can be either of GDS or CIF, all kinds of the standard files. So the easiest we are processing mostly is Zapper resist, PA, and the N, and HQ will be provided by the users usually because the shut time is very short. So really, by the they demand, then we get the HSQ and then process the job. The resolution for all these we can probably can achieve under 20 nanometer resolutions. Let's give you quick examples of the structures made here. This is silicon nanowire guide applications. So on the SOI, standard SOI, have a 220 nano of SOI layer. So you do the etching, use the DIE, and get the about 4 to 5 dB per centimeter, which is almost the same as the structure made by Cornell Nanofab. This is a grading structure. You see, they have a very small features on the right. So these ones is provided by Professor Helm's group. So as you see, features here is 4 micron. I think here is maybe 100 nanometers of the grading structures. We also did recently did some of the waveguides based on the silicon oxide nitride or silicon nitride for visible applications. Some application will be in the sensors, the photon sensors. So this one is the silicon oxide nitride waveguide. It gives a very nice it's 1 to 1 dB per centimeter. It's a really nice waveguide. And this one, we use the silicon nitride, LPCV silicon nitride grow here, and the pattern use E-beam and use DIE silicon nitride etching recipe. Make a really smooth etching on this. And this the first try still get 2 dB per centimeter loss. So it's we can right now can accept all kinds of jobs for silicon and photonics research, because all the photonics research the base structure is the waveguide, and you can combine the ring oscillators or the photonic crystal structures. All these structures requires nano resolution and precise and control of the etching, especially there's a control of the sidewall smoothness. If you any request or any concerns, you can contact me or go to our website at tnfc.geotron.ca. Thanks.
much, Edward. Very interesting content. Well, the continuing passed on to Aaron. I'll field a question here from the audience. It asks for a comparison between E-beam and focused ion beam, so perhaps Edward and Aaron could speak to this one. For gratings that require spacings less than 10 nanometers, what's the better method, E-beam lithography or FIB?
Depend what's the material that is interested in being patterned. That's think about. I think this is something that maybe we could do online. I think it'd be more important to get some more details about the exactly what the pattern they have in mind, like this and the the thickness of the etch depth, things like that. I think meters are this is for less than 10 nanometers. Was that right? For under 10 nanometers, I'd say this actually probably goes. It's a good segue into my next section. You'd really think with a very small spot size, and really a helium ion beam, focal ion beam would be a good approach to use in that case. So if I might just that and discuss some of the work that we've done at NanoFab with using our new dual beam helium and gallium focus ion beam tool. So this Zeiss Orion NanoFab tool, no relation, that we've recently installed in our facility. The installation happened late in 2015, and we are currently in the process of qualifying qualifying different applications. This is the tool itself. Now, according to speaking to this question, the helium ion spot size itself is only about half a nanometer in diameter. This gives you sort of unparalleled resolution for helium ion imaging, and also allows you to do very small features, very small side of things. Here I've got an example from the small or the large and small kind of scales of volume that's being removed. Here we have a 30 nanometer thick silicon nitride membrane for ink, in which we're able to pattern from the using the helium ion beam a sub 10 micron nanopore. So this is a single pore through this membrane. It's about just over 5 nanometers in diameter. Side of things, if we want to, we can gallium fib beam to remove large volumes of materials. So, an example of EM specimen preparation using the fib. So, using a high energy, high beam current, we can this large amount of volume of silicon, and gradually, it's a little bit difficult to see here, but you can see there are kind of different toes as we've gone to lower and lower beam current for the gallium to do finer and finer polishing, and we could even go to the helium ion polishing at the end if necessary. So this is thinning it down to a grain which is transparent to electrons. That's about 100 nanometers or so. Now, as I mentioned, we are still in our very initial qualification stages of this qualifying application work for this tool. So I've got a couple of pretty pictures to show, though. For helium ion milling, we've got some silicon nitride double nano beams. This is from the EVOI group at the University of Alberta. So this is an example of what you might be able to do with this tool to modify a structure after it's been made. So removing this large amount of material to define the beam itself. This is something which could be more appropriately done using E-beam lithography, possibly even photolithography, depending on your size. But after that, we can put it into our helium tool, and mill very fine features. So here's a Happy New Year message that we had January. But maybe to illustrate the beam divergence a little bit better here, we've got these, I think, approximately 20 meter diameter holes that have been milled through this nitride nano-beam, and you can see that there's eligible beam divergence have exactly the same size hole as we can tell underlying silicon substrate, which is some microns away. So just a last example. This is the milling is really a grayscale technique. I mean, you aren't limited to only vertical sidewalls. It's very easy to pattern arbitrary rectangular, shown here, or radial profiles using both the gallium and the helium milling. The hardware software we have for that is the NPVE engine by Phibix out of Ottawa. So, in addition to sort of mathematically defining what kind of this might be interesting for instance, making a zone plate in silicon, or you could do this in gold. It's also very easy to digitize grayscale images, bitmap images, in which the grayscale value will be transferred to a milling depth. So you can choose either black is no and white is full milling to the full depth, or vice versa. So we've sort of done a micro-portrait of Carl Zeiss to illustrate this. Now, this was, as you can see, it's not as if it's a cameo Zeiss himself. This is not a sculpture as you might see on a coin, but when viewed in normal, you get the colors right. So that's just an example that was done by my counterpart for on the characterization side of things at NanoFab. So I'd like to acknowledge the NanoFab staff, funding agencies, and then for any either fabrication or characterization services, please feel free to contact either myself or Peng Li. Thank you.
Thanks. There's a question that came in about FIB, so I'll pass that on to you. Now, the question is FIB used in any commercial applications or in production mode?
Yeah, I believe, let me see. I believe FIB was originally used largely for IC production, like for, I mean, not actually mini ICs, but for mask surgery. You can do some surgery on circuits to fix errors. You can do wafer scale, step and repeat type of fibbing. So, for instance, our tool, we haven't explored the side of it yet, but it is possible to put in a larger wafer and pattern a die at periodic spacings across a wafer, for instance. So, if that's sort of thing you're interested in, yes, it would be possible to make hundreds of die across a wafer using FIB.
Okay, thanks.
Yeah.
Now, I'd like to invite the audience to stay connected with CMC Microsystems for news about the next webinars in this series. The second webinar coming up later on in the spring is entitled "A Micron Wide and 10 Angstroms Deep, Metrology and Materials Characterization." For information about how fact services can support your technology development, I welcome your contact, and I would direct your attention to visit the fact services webpage down here at the bottom to join a discussion forum where you can ask about specific processes and capabilities within the FACT network. Also access a recording of this presentation. So any questions that didn't get addressed today, or that you want more detail and discussion on, this would be the perfect place to do it. So there were some other questions that I saw come in, but we're out of time, so I'm going to refer those discussions to the online forum. And with that, I thank you all for your participation. This concludes the webinar.